This video will provide a short introduction to sets. Why do we care about sets? First of all, the expressive power of sets is nearly unlimited. We can describe almost anything using sets. In many applications, sets will be used to describe parts of a decision problem. For example, the collection of all outcomes that are possible in a strategic interaction can be described as a set. The idea of a set is intuitively simple. So we have this incredibly expressive language of sets, yet the idea of a set is intuitively simple and easy to understand. Finally, sets are precise mathematical objects. This means that we can communicate our ideas accurately using the language of sets. So what is a set? Roughly speaking, a set is just a collection of entities. The entities that make up a set are called its elements. So we will have to become a little bit more precise, but roughly speaking, a set is a collection of entities, and those entities are called the set's elements. If lowercase x is an element of the set capital X, then we have an expression to indicate that in symbolic notation. And the symbol that is used is similar to the letter E, which reminds us of the word element. We may also say that lowercase x is in capital X, although the word in may at times be used for other purposes. So this would have to be deduced from the context. So we like the word in because it is very short, but it may be used for other purposes, so just be careful when we see the word in. We may also say that lowercase x belongs to capital X. And we also have a synonym for the word element, and that synonym is member. So there are several ways of indicating membership in a set. The first of these is to say that lowercase x is an element of the set capital X. We can also use symbolic notation. We can also say that lowercase x is in capital X. We can say that lowercase x belongs to capital X. We can also say that lowercase x is a member of capital X. Okay, so how does one go about defining a specific set? There are three ways. The first is to define a set by listing or enumerating all of its elements. The second way is to define a set by characterizing set membership. The third way is to define a set by applying set operations to sets. So these are the three ways. We will go through them one by one. The simplest way to define a set is by enumerating its elements. This means listing its elements in any order, separated by commas, and enclosing the list between a pair of matching curly braces. Listing and enumerating are synonyms. Now here's an example. We have a set with the elements 44, S, %, D, A, and a sharp sign. The opening curly brace indicates that we are beginning to define the set. The closing curly brace indicates that we have finished defining the set. And of course, 44, S, %, D, A, and the £sign are elements of the set defined in the example. Like almost anything else, sets can be given symbolic names. We often use symbols to refer to mathematical constants. For example, we sometimes use the letter capital G to indicate the gravitational acceleration on our planet, 9.8 meters per second squared. Well, we can give sets symbolic names if it is convenient to do so. For example, here we are using the symbol S to denote the set with these elements, A, B, C, D, E. Now, instead of saying the set with elements A, B, C, D, and E every time, we can just refer to the set S. So that is sometimes convenient. There's a special set, and that set is called the empty set. The empty set is special because it has no elements. And it can be defined by enumeration in the very obvious way as a list surrounded by curly braces. Of course, this list is empty because there are no elements in the empty set to list. The empty set is more commonly denoted by a special symbol that looks like a 0 with a line going through it. So the empty set is a special set that has no elements. A set is a collection of entities that are called its elements. Sometimes that collection may be empty, and in that case the set is called the empty set. Now here's a very important principle that we want to remember. A set is defined only by what its elements are. This is why the order in which one lists the elements of a set does not matter. Also, this principle indirectly says that listing some elements more than once does not change what the set is. So, this means that, as in this example, the set with the elements 1, 2, and 3 is the same as the set with the elements 1, 2, 2, 3, 3, and 3, which is again the same as the set with elements 3, 2, and 1. These threes are all identical. They are the same. They are not in there more than once. They're in there exactly once, but we can write the 3 multiple times. Now, the very important principle that we just saw can be restated as follows. Two sets are equal if every element of one is an element of the other, and vice versa. So the very important principle that we just saw is really a statement about when are two sets the same. More precisely speaking, sets A and B are equal if both of the following are true. Every element of A is an element of B, and at the same time, every element of B is an element of A. So when we go back to this example, we can see that 1, 2, and 3 are in this set, and 1, 2, and 3 are also in this set. 1, 2, and 3 are also in this set. And we can see that nothing other than 1, 2, and 3 are in each set. So the elements that are in each set are the same. So the 3 sets are the same. So precisely speaking, sets A and B are equal if both of the following are true. Every element of A is an element of B, and at the same time, every element of B is an element of A. The second way to define a set is by characterizing set membership. This means that a set can be defined by writing down a condition such that both of the following are true. Every entity that satisfies the condition is an element of the set, and at the same time, every element of that set satisfies the condition. Such a condition is said to characterize membership, in that set. So here's an example that should make clear what we mean. So we have here a definition of a set. It is the set of all x such that x is an odd number smaller than 10. So as we did when we defined the set by enumeration, we start defining the set by using the opening curly brace. And then we say x, or some variable, such that x satisfies some condition, and then close the curly braces. The set in the example is equal to the set with the elements 1, 3, 5, 7, and 9. That's because when we replace the x in this condition, x is an odd number smaller than 10, with each of these numbers, the statement becomes true. Nothing else that we can put in there to replace x makes the statement true. If we plug in anything else besides these 5 numbers, the statement will become false. So this is a condition that characterizes membership in this set, and this set, the set of all x such that x is an odd number smaller than 10, is equal to the set with the elements 1, 3, 5, 7, and 9. The symbols used to indicate the variables that must satisfy the condition for set membership can be arbitrary. This means that the following sets are all equal. We could write the set of all x such that x is an odd number smaller than 10, the set of all y such that y is an odd number smaller than 10, the set of all delta such that delta is an odd number smaller than 10, or the set of all Chinese characters for a character for horse such that the Chinese character for horse is an odd number smaller than 10. So here's an opportunity to test yourself. Why don't you try defining the empty set by characterizing set membership? And of course, there is more than one answer. The third way to define a set is by using set operations. And we can define a set by applying the following set operations to several sets. We can use union, intersection, difference, product, and exponentiation. Again, we will go through these 5 different set operations one by one. The first is union. Now, the following lines represent different ways of writing down the same set. We can say the union of A and B. We can say A union B. Or we could use this symbolic notation, A with a U-like symbol in between and then B. Or we could use a definition of a set using a condition that characterizes set membership. So we could write this set as the set of all x such that x is in at least one of the 2 sets A and B. Okay, so here's an opportunity to test yourself. Let capital X be the set with these elements, 1, 3, 5, 7, and 9. And let Y be the set with these elements, 2, 3, 5, and 7. Now, verify for yourself that X union Y is equal to the set with the elements 1, 2, 3, 5, 7, and 9. So let's pause for a moment and try to verify that this is the case. Are you convinced? Intersection is the second set operation. The following lines represent different ways of writing down the same set. The intersection of A and B, that's the same thing as A intersect B. That's the same thing as A and this upside down U symbol between A and B. And then finally we have this expression, the set of all x such that x is in both A and B. So this is what an intersection of the two sets A and B is. So here's an opportunity, yet again, to test yourself. Here are the two sets, x and y. These are the same as before. X is the set with the elements 1, 3, 5, 7, and 9. And y is the set with elements 2, 3, 5, and 7. Now verify for yourself that x intersect y is the set with the elements 3, 5, and 7. The third set operation is difference. Again, the following lines are different ways of writing down the same set. We can say the difference between A and B. We can say A minus B. And we can also write A backslash B using symbolic notation like this. And we can also write the set of all x such that x is in A but not in B. Again, let's see an example. You can test yourself. Let x be the set with elements 1, 3, 5, 7, and 9. And let y be the set with elements 2, 3, 5, and 7 as before. And verify that x minus y is equal to the set with elements 1 and 9. And also verify that y minus x is the set with one element, which is 2. And after you verify this, can you explain why x minus y equals x minus the intersection of x and y? If you can, you probably understand what set difference is. The fourth set operation that we want to talk about is product. Here's an example of a product of two sets. You can take the product of more than two sets, but we're going to start with two sets. The following lines are different ways of writing down the same set. We can say the product of A and B. We can say A times B. Or we could write that in symbolic notation like this. Or we could also write the set of all ordered pairs x comma y such that x is in A and y is in B. We could also take the product of n sets, n being some natural number. So we could have the set of the product of sets A1, A2, A3 all the way up to AN. We can write that as A times A2 times A3 times so on up to AN. We'd also write that in symbolic notation like this. Or we could also write the set as the set of all ordered n tuples A1 through AN such that A1 is in A1 and A2 is in A2 and A3 is in A3 and so on all the way up to AN is in AN. Now, to understand set products, we need to understand what n tuples are. An n tuple is an ordered list that is n items long. It's important that you remember that an n tuple is an ordered list, and that list is n items long. The elements of A times B are two tuples, and two tuples are sometimes called ordered pairs. The elements of A1 times A2 all the way through AN are called n tuples. An n tuple is not a set of the n items in the list. We can see this from the following example. The 3 tuple, 1, 2, 3, is not the same as the 3 tuple 3, 2, 1. That's because it is an ordered list, so the order in which things are listed matters. And 3, 2, 1, the ordered 3 tuple, is not the same as the ordered 4 tuple 3, 2, 1, 1. Again, unlike a set, repetition matters, order matters. So an n tuple is an ordered list that is n items long. And when you take the product of n sets, you get a set whose elements are n tuples. Okay, so here's a way to test yourself on the definition of set products. Here are 3 sets. The set X has 2 elements, 1 and 2. The set Y has 2 elements, capital T and capital F. The set Z has 2 elements, the plus sign and the minus sign. Now you should check for yourself that X times Y is equal to the set with these 4 ordered pairs. 1 comma T is an ordered pair. 1 comma F is an ordered pair. 2 comma T is an ordered pair. 2 comma F is an ordered pair. And we can see that the first part of each ordered pair comes from the set X, which comes first in the product. And the second part of the product, Y, well, the second part of the ordered pair comes from the set Y, which is the second part of the product. So T is in Y, F is in Y, T is in Y, F is in Y. 1 is in X, 1 is in X, 2 is in X, 2 is in X. And we can also check that Y times X is equal to the set with these 4 ordered pairs. T comma 1, T comma 2, F comma 1, F comma 2. So we can see that the first part of each ordered pair in the set comes from the set Y. See, T comes from Y, T comes from Y, F comes from Y, F comes from Y. And that's because Y comes first in the product. And the second part of the ordered pair comes from the set X. 1 comes from X, 2 comes from X, 1 comes from X, 2 comes from X. So that's because the second part of the product is the set X. We can also look at a product of 3 sets, X times Y times Z. Because you're taking the product of 3 sets, you are going to get a set whose elements are ordered 3 tuples, sometimes called ordered triples. So we have 8 elements in this set, 1 comma T comma plus, 1 comma T comma minus, 1 comma F comma plus, 1 comma F comma minus, 2 comma T comma plus, 2 comma T comma minus, 2 comma F comma plus, 2 comma F comma minus. And we can see that the first part of each ordered triple comes from the set X. 1, 1, 1, 1, 2, 2, 2, 2. These are all elements of X. The second part of the ordered triple comes from the set Y. T, T, F, F, T, T, F, F. These are all elements of the set Y. The last part of the ordered triple, the third part, always comes from the set Z. Plus, minus, plus, minus, plus, minus, plus, minus. We can see that these are the elements of the set Z. The last set operation that we want to go over is exponentiation. So these are all ways of writing down the same set. B raised to the A power, or we could write in symbolic notation like this. We could also write down the set of all f such that f is a function that maps A to B. Now, this definition obviously is going to hinge on the definition of a function. So knowing what a function is very important to this definition. In fact, knowing what a function is and how to define one is about 1,000,000 times more important than understanding exponentiation. So let's actually get to the definition of a function. A function that maps set A to set B assigns an element of B to each element of A. This means that every element of A gets mapped to exactly one corresponding value in B. Now don't be confused. It is possible that multiple elements of A map to the same element in B. What's not possible is that a single element of A maps to multiple elements in B. See, that's because every element of A gets mapped to exactly one corresponding value in B. It's possible that some element of B has no element of A that maps to it. So every element of A gets mapped to exactly one corresponding value in B, but there are some values in B possibly that don't get mapped to. It's not possible that some element of A maps to no element in B. Every element of A gets mapped to some element in B. All right, so let's talk about defining a function, defining a particular function. So let S be the set of students in this course that I'm going to call Ann, Bob, Chuck, Dave, and Frank. And let G be the set of grades that these students may receive in this course. And the grades are A, B, C, D, and F. We can define a function from the set S to the set G in several ways. The most straightforward way is by using equations. We need an equation for each element of S. So we have f of Ann equals A. That means Ann maps to A. We have f of Bob equals B. This means that f maps Bob to B. F of Chuck equals C. F of Dave equals D. F of Frank equals F. So we have 5 equations, one for each element of S. We may also use pictures or tables. For example, we might use this picture here. We have the set S depicted on the left here, the set G depicted on the right. And we can see that there's an arrow mapping Ann to the grade A. There's an arrow mapping Bob to the grade B. There's an arrow mapping Chuck to the grade C. There's an arrow mapping Dave to the grade D. There's an arrow mapping Frank to the grade F. And we can also use a table like this. We can have a column for different inputs which have to be in the set S. And we might indicate that by the variable X here. So we have these inputs Ann, Bob, Chuck, Dave, and Frank. And we have the outputs, which is F of X. So the output that corresponds to input Ann is A. So F of Ann is equal to A. The output that corresponds to Bob is B. The output that corresponds to Chuck is C. The output that corresponds to Dave is D. The output that corresponds to Frank is F. So we can define a function by writing down some equations. We can define a function by using a picture. We can define a function by using a table. We can define a function also as an n-tuple if the function is from A to B and n equals the number of elements in A. For example, the function f from S to G can be written as the ordered 5-tuple A, B, C, D, F. And in this 5-tuple, we have to say what the coordinates mean. So in this 5-tuple, the first coordinate is the value of f of Ann. The second coordinate is the value of f of Bob. The third coordinate is the value of f of Chuck. The fourth coordinate is the value of f of Dave. And the final coordinate is the value of f of Frank. Now, you can use a different order, but you have to be clear about the meaning of each coordinate. As long as you indicate what each coordinate indicates, you can use a different order. But of course, the order matters because you have defined what each coordinate means, right? A function from A to B can also be defined as the set of n ordered pairs where n equals the number of elements in the set A. Now, the function f from our example, from S to G, can be written as follows. So it can be written as the set of 5 ordered pairs, Ann, A, Bob, B, Chuck, C, Dave, D, Frank, F. So each of these ordered pairs represents one of the arrows, mapping Ann to A, Bob to B, Chuck to C, Dave to D, and Frank to F. Okay, so now we have finished talking about the different set operations. So we know about the 3 different ways to define a set. Now I want to move on to the topic of subsets. The following lines mean exactly the same thing. A is a subset of B. That means exactly the same thing as this symbolic notation, which looks like A and a sideways U with an underline, B, which means exactly the same thing as every element of A is an element of B. Now, if every element of A is an element of B, the collection B is at least as large as the collection A, right? That's exactly the idea that we want to capture by saying that A is a subset of B. So here's an opportunity to test yourself again. The following 2 lines are logically equivalent. Can you explain why? The line A equals B means exactly the same thing as saying A is a subset of B and at the same time B is a subset of A. And if you go back to the very important principle that we discussed earlier, this will become clear. So why don't you try that? Now here are some important facts about subsets that I want to go over. And here are 3. Every set is a subset of itself. So this means that if A is a set, then A is a subset of A. The empty set is a subset of every set. That is, if A is a set, then the empty set is a subset of A. Finally, if a set has capital N elements, then it has 2 to the capital N subsets. These facts will be useful to remember. So again, here's an opportunity to test yourself. Here's a set with 3 elements X, Y, and Z. This set has exactly 8 subsets, and those 8 subsets are the empty set, the set with 1 element X, the set with 1 element Y, the set with 1 element Z, the set with 2 elements X, Y, the set with 2 elements X, Z, the set with 2 elements Y, Z, and finally the set with 3 elements X, Y, Z. Can you explain why this is correct? If you can explain why this is correct, then you understand the definition of subsets, most likely.